Become a sustaining member of the Commonwealth Club for just $10 a month.
So welcome everybody. I really like this room. I like this room better than the big room. It's definitely more intimate. And thank you for that introduction, Gloria. I've been doing programs for the Commonwealth Club for, oh gosh golly, a long time. And this is a really special one. Lawrence Livermore has a very special place in my heart because Herb York, who was a close friend of my grandfather, Herb is the reason I ended up in California as a little child at UCSD. So, I didn't go to UCSD, you know what I mean. My mother did. So anyway, so this is going to be wonderful. And also, I run a podcast. I've been a long time science and tech and healthcare journalist, mostly for the New York Times, and mostly but these days I run a podcast called Lost Women of Science, where we're busy snatching women from the jaws of historical obscurity. Our mantra is, we're not mad, we're curious. Okay, we're a little mad. So what I'd like to say is, thank goodness this fate will not befall you. I'm quite sure of it, given the advances we've made in women in STEM in the last few decades. So I encourage everyone to learn more about the club's offerings at www.commonwealthclub.org. And I am so pleased to be here with Kim Budell, the director of Lawrence Livermore, as we know. And Lawrence Livermore, as many of you must know, I'm curious, how many people here are scientists? A good number. How many are physicists? Okay. Oh, good. Got one. Yeah. Yeah, good. I think this is good. This is going to help us with the language barrier. What happened in December of 2022 was really very significant. When Lawrence Livermore made national news, when it achieved self-sustaining fusion ignition for the first time, a potential breakthrough for the production of clean energy. And I can't wait to discuss all of this. First, a little background about Kim. She's the 13th director of Lawrence Livermore, the first female director, not surprisingly. She's an applied physicist, specifically an expert on high energy density science and laser experiments. She's held numerous technical and leadership roles at Livermore. She served on assignment as a scientific advisor in the Department of Energy and was the vice president for national labs at the UC Office of the President. You're a graduate of UC Davis.
Yes.
But where did you get your PhD?
So I got my PhD in applied science from UC Davis through a department where they had a physical presence actually at Livermore. So I did my dissertation research at the lab.
Are you a native Californian?
No, I grew up in Chicago.
Got it. Okay. Well, welcome anyway.
I guess now I am. I've lived here longer than I lived in Chicago.
Yeah. Okay. Well, it's case closed. So nuclear fusion, just a little bit of a primer, and correct me if I'm wrong. I got this from GPT, kidding. Nuclear fusion, an emissions-free form of energy generation that has long been viewed as the holy grail of energy, took important steps toward this reality under your watch at your place late last year. What happened was that Scientists crossed a major threshold known as ignition, creating a fusion reaction that generated more energy than it took to produce, which is hugely important versus fission. So let's talk first of all about the difference between fission and fusion, if you don't mind.
No problem. So most people are familiar with fission. So in fission, a heavy atom breaks into two pieces and releases energy as part of that fissioning process. So this would be uranium as an example, as a fissionable material. And so in a fission reaction, once you start the process of breaking apart nuclei and releasing this energy, the neutrons that are released hit other nuclei and break them apart, and you get what's called a chain reaction. In fission, I'm already on a bad track here. In fusion, what do we do again? In fusion, you take two very light nuclei and you squeeze them together and get them to form one nucleus and release energy through neutrons. So in nuclear fusion, you typically have hydrogen isotopes, so heavy hydrogen, deuterium and tritium. You squeeze them together at very high pressures. If you can get them to high enough pressures and hold them together long enough, they fuse together and they form a helium atom and release a neutron that carries energy away. The beauty of fusion, if you can make the reactions go, is that when you take the pressure off, the fusion stops. So many of the concerns you have about a runaway chain reaction and the fission reaction it's not possible in a fusion reaction. The trick is it's very hard to push atoms together that hard and hold them together long enough to get them to fuse.
So, and fusion got a very bad rap after the atomic bomb was developed. Then Teller and others started work on the hydrogen bomb, which was X number of times more powerful than the atomic bomb. And so I sort of went through my childhood thinking first two things about fusion, bad, and Teller was kind of a bad guy, and also really, really hard to obtain in a way for peaceful means. Is that right, or was I
Well, certainly the part about hard to obtain for peaceful means. So fusion is the process that fuels the sun. So it's a naturally occurring process in the universe. And the way the sun generates self-sustaining fusion reactions is with gravity. The sun is very big, there's lots of gravity that pushes the hydrogen together and creates the self-sustaining fusion engine. So I would say fusion is not bad. On Earth, the only place we've been able to generate fusion reactions of this kind prior to this event is in operating nuclear weapons, where the energy densities are high enough. So thermonuclear weapons are based around nuclear fusion. So the goal for the last 60 years has been trying to be able to create those conditions in a laboratory setting so that you could study them and understand them and potentially use it as a building block for an energy source.
And how continuous, how ongoing has the research been?
It has been pretty continuous. There are two flavors of fusion research. We do what's called inertial confinement fusion. So we try to very rapidly compress a very small amount of fusion fuel in a capsule and get it to ignite. There's also magnetic fusion approaches. In a magnetic fusion system, you use a really big, typically it's a torus, a donut-shaped vessel that has magnets around it that confines a very low-density plasma for a long time. So very different. The timescales are very different. The conditions under which we operate are very different. But in both cases, the goal has been to get a reaction going that produced more energy than it took to drive the reaction.
So, and you guys used this thing that was the size of a pencil eraser, right?
Yeah.
So it's this tiny little capsule.
Yeah.
And tell us exactly how I love getting insight into sort of the scientific process, like the iterative process. So just, can you give us a thumbnail on how it progressed?
Sure thing. And at the end, we'll come back to how close are we to fusion energy. I'm confident we'll get back there. So early on in the program at Livermore, one of our researchers set about trying to find a way to create these fusion conditions in the laboratory, where you could do it under controlled experimental conditions and really study the physics of these fusion plasmas. A gentleman named John Knuckles, who's still working. He has an office right down the hall from me. He had an idea that this new technology that had just been invented, lasers, could potentially be that energy source. So if you could use the lasers to create a light field that would push on a small capsule, they would be able to blow off the outer surface. That causes the inner surface to move inward, which would allow you to compress that fusion fuel up to very high temperatures and densities. So when John made those initial predictions, their guess was it would take about 1,000 joules of laser energy to achieve fusion ignition. So spoiler alert, it took more than 2 million. So we were not close. John was thinking in one dimension because we had very rudimentary computer codes. We had very limited understanding of how plasmas work. And plasmas do not want to be compressed. They're made up of charged particles that want to blow apart. So everything about creating a fusion plasma works against the natural instincts of how the plasma would behave. So the lab set about building a laser to try to test some of the hypotheses that this team had made. And they built the first lasers at Livermore that were a few hundred joules, then a few thousand joules, and then tens of kilojoules. And finally, in the late 90s, we broke ground on what would become the National Ignition Facility.
So we're not talking like a laser pointer with a huge
No.
honking.
No. So when I came to Livermore in the late 80s to do my dissertation research, I worked with tabletop lasers and did experiments. And you could spend all day aligning your laser and getting ready to do, your experiment. It was incredibly fun, but very challenging. Across in the next building from me, the NOVA laser, which was the precursor to NIF, was operating. So NOVA was a 10-beam laser facility that produced 40,000 joules of laser energy, which was at the time the world's largest, most energetic laser. And this thing was massive. It filled, like the laser hall was the size of a football field. When they took me over and showed me the laser, said, okay, we use this giant laser, and we have these 10 huge beams, and we focus them into this big target chamber onto this little tiny target. I laughed. It seemed crazy. This can't possibly work. It's so hard to be so precise, even when you have hands-on control of all the variables. But they had done it. So at the National Ignition Facility, we scaled that laser up, and scientists at that time made a proposal to a committee from the National Academies that was looking at the prospects for fusion, that they believed it would take a 10 megajoule laser as the next step to confidently achieve fusion ignition in the laboratory. So go from 40,000 to 10 million joules. The National Academy said, too big a jump, too big a leap in technology. So the ambitions were scaled back to about 2 megajoules. And they said you have 3 basic challenges. One is making these little targets maintain their very spherical shape as you implode them. One is stopping little instabilities on the surface of the target from growing and putting cold material into the hot fusion fuel. And the third is getting all that laser energy into a little tiny can, which creates an X-ray bath that actually illuminates the outside of the capsule and starts the implosion reaction. So the NIF was decided to be built at 2 megajoules, and that project took about 10 years to complete. Started operating at full power in 2009. So the NIF facility, the cross-section is 3 football fields in extent, and the facility is 10 stories tall at its greatest extent. The target chamber where we do the experiments is 30 feet in diameter. It's surrounded by a room that has concrete walls that are, 6 or 7 feet thick to contain the neutron irradiation that was expected from these experiments. The capsule assembly, the little target where we make these reactions happen, is a little gold can that's about a centimeter long. In the center of it is a small diamond capsule that's a couple of millimeters in diameter.
Why diamond? People must ask you that a lot.
Well, because gold holograms and diamond capsules is what everyone wants. The initial point design that we started with at the National Ignition Facility was plastic. The capsule material is plastic. Plastic can be made very easily in the shapes that we needed. You can get very uniform material with plastics, the way we grow them. And you can put dopants in the plastic that help keep stray X-ray radiation from getting in to the capsule and preheating it, making it harder to squeeze to high pressures. Turns out that in order to implode plastic capsules, you needed a relatively long laser pulse. When you shine the laser pulse into this little gold can, it creates a plasma in the holes where the laser comes in, just from the gold blowing off the can wall. As that gold blows in, it becomes a mirror, and it reflects the laser light back out of the can, which is bad for many reasons. One, it's a lot of laser energy, and it could, damage the laser. But it means that you don't get the amount of energy into the can that you need to create the temperatures and the X-ray conditions required to squeeze up that little capsule. With diamond, it's harder to make the capsules, but because of the characteristics of the material, you can use a shorter laser pulse. So it's easier to get all the laser energy into the can and get the capsule to the right conditions. The material is much harder to control. So a lot of our early attempts with the diamond capsules had problems with what we called meteors, imperfections in the capsule, putting cold material right into the center of the fusion fuel. So when I say long pulses and short pulses, the long pulses were about 4 nanoseconds, so 4 billionths of a second. The short pulses are about a nanosecond or a little more, so a billionth of a second. So everything's pretty short, but it's relative in this case. Mm-hmm. So we started doing experiments. The initial experiments with the plastic capsules produced very, very small amounts of fusion yield. It turns out it's not very hard to create some fusions. It's very hard to create this self-sustaining sort of bootstrapping reaction in the fusion fuel. So maybe a few thousand joules of fusion energy came out. This was during what we call the National Ignition Campaign. Eventually, it was determined that these capsules, based on all the experimental data we were taking, were not going to get to the conditions that we needed to achieve ignition. So a second team was chartered from our national security program to come in and take a different look at the target physics. And what they decided was that all the little bumps and wiggles on the surface of that capsule were actually a big part of the problem, because as the capsule moves inward, those perturbations tend to grow. And that material's cold, and so as soon as it gets into the fusion fuel, it turns the fusion off. So they said, well, what if we step back and change the shape of the laser pulse so that we could be sure those little perturbations didn't grow? We would just create conditions where the capsule was very stable. It definitely won't ignite because we won't get as much push on it, but we can test this hypothesis. As soon as they started making those capsules more stable, the fusion yield started going up. So we knew we were on a track to begin to take the physics apart and make progress. Again, because of the characteristics of the laser pulse and the gold can, which we call a hologram, that holds the fusion target, it was clear that we needed to change other things in order to get to conditions that would actually ignite those capsules. So that was the shift to diamond. And it's a really incredible partnership between people doing modeling and simulation, very high fidelity simulations of what's going on in the capsule, very high fidelity simulations of how the laser energy actually gets into that can and turns into X-rays.
And Tiffany.
So we can understand those processes. And then a huge array of diagnostics. So the other great story of that decade is that we continued adding new diagnostics to the experimental facility so that we could learn different things about what was happening in these capsules. We put cameras so that you could take pictures of that very dense core as it came in and see exactly what was happening. That's how we found out we had these meteors shooting into the center. We put on diagnostics to look at the charged particles that come out of the target. And so you get a very clear indication that the neutrons that were coming out were not symmetric. You might expect, if it's a spherical target, and you get a spherical fusion hotspot in the center, that the radiation that comes out should just come out in a uniform bath. Well, it wasn't. It was aiming in one direction preferentially. So it was clear that we had some kind of asymmetry in the way the fuel was coming together. So using this, rich wealth of data from the laser and from the experimental diagnostics that we had, and improving our models using things like machine learning to, ingest all this data and make the models more predictive. When we actually did the experiment that ignited, the models had predicted that we had a better than 50% chance of igniting that capsule.
And were there other labs around the country or around the world? Was there any kind of race of any kind going on?
So not domestically. We work with many other laboratories, and there are many groups pursuing fusion research across the country. For inertial confinement fusion, we are the biggest game in town. So the National Ignition Facility is really the flagship facility for the whole community. And we work with researchers from around the world on these experiments. Other countries are building big laser systems and have challenged us. The Russians have built a large laser system. China has plans to build a large laser system. We have a collaboration with France. They are building a laser megajoule, which will be a little bit smaller than NIF, but it was started about the same time and used much of the same technology and supply chain. So that was a really fruitful partnership to tackle some of the big engineering challenges required to build this laser.
So I want to get to this question of how close we are to fusion energy, but I want to do it circuitously by way of what the National Ignition Facility's charter is, which is it's to benefit scientists who are working on the nuclear stockpile.
That's right.
I mean, weapons are the number one. Okay, so now that we've gotten that out, how does one reconcile that with what we would actually, I'm sure all of us in this room love to see someday, to heal our critically ill planet? So let's for a minute forget about the weapons.
That's a good story too.
It is a good story. I mean, if you want to address the nuclear stockpile, which
No, I'll just say, so in the late 90s, when the decision was made to cease underground nuclear testing, the U.S. embarked under President Clinton on what was called the Stockpile Stewardship Program. And the goal was to create a set of scientific capabilities that would allow us to ensure the safety, security, and reliability of the U.S. nuclear deterrent without nuclear testing. So this is the 30th anniversary this year of the last nuclear test that the U.S. did. And so what this program did was drive a revolution in supercomputing, in modeling and simulation, in experimental capabilities to increase our knowledge of the component physics and engineering of nuclear weapons so that we would not be in a position where the U.S. had to resume nuclear testing. And I would say we have been spectacularly successful on that front. And this foundational capability for our national security remains viable and better understood today with a new generation of people who've joined the program since the end of nuclear testing, which is a great benefit to the international community that the U.S. has been able to step away from nuclear testing and sustain this nuclear security component. And I think what's happened in Ukraine has brought home to us again just how complex and difficult the international security environment is today, particularly nuclear security. And so this is, I would love to live in a world where the conditions exist where there would be no nuclear weapons, and we don't live in it today. And so I'm proud that we've made this progress and that we've been able to ensure that the U.S. can have this essential capability without nuclear testing.
And how does Lawrence Livermore, which is, as I understand it, under the aegis of the University of California and the federal government, Is that right?
We're what's called government-owned, contractor-operated. So for most of our history, we were operated by the University of California, full stop. Since about 2007, we've been operated by a limited liability company, where UC is the major partner in partnership with Bechtel National. And currently the full industrial partnership includes Amentum and BWXT.
So what is the direction going forward for fusion energy in another context?
Yeah. So the thing about fusion, well, the old saw about fusion is that fusion energy is 50 years away from whatever day you ask.
Right. That's what we all kind of...
And, you know, that's a legitimate complaint. It's been pretty true. The fusion community I also describe as sort of like a plasma. It tends to blow apart. It's an incredibly hard problem, and there are a lot of big ideas and passionate people in the community. And so, you know, progress is complicated. In inertial confinement fusion, it's been very complicated for a long time. There were many people who said that it was impossible to ignite a capsule at the National Ignition Facility. So it takes a special kind of passion for mission to pursue something like this. So what I would say today, you know, the fundamental building block for an inertial fusion energy scheme is an igniting capsule. So we have demonstrated the plausibility of inertial fusion energy. We are very distant from an inertial fusion energy system.
Got it.
So we put 2 megajoules, just over 2 megajoules of laser energy into that target and produced 3.15 megajoules of fusion yield. So that's the first time ever an experiment has put out more fusion energy than the energy required to drive the experiment. Now it took 300 megajoules, roughly, to drive the laser. So that's wall plug break even. NIF wasn't built to be an energy machine. It was built to be a scientific facility. So the laser's not very efficient. It's a couple of % efficient. It's easy to look at newer technologies where lasers can be tens of % efficient. So that could be improved dramatically. We've been working very hard to understand the physics of these very complex plasma systems for a long time. We have the world's most complicated target, you know, cooled to cryogenic temperatures, precisely engineering marvels of the universe, works of art, little tiny works of art, to get ignition once. You know, we really need to get the gain up in that target. So this was a gain greater than 1, but we need gain of 50, say, to begin to move toward break even. And we need those capsules eventually to be cheap to produce. Oh, and you have to make ignition 10 times a second, not 1 time a week.
Right.
So there's a few details to put out there.
Gosh.
But
I'm sorry.
and it's not to say that it's just engineering, but before you could ignite 1 capsule, it wasn't plausible to start thinking seriously about a fusion energy system
Right.
based on inertial confinement fusion.
How many people at Lawrence Livermore are working on it?
So we have a few hundred scientists and engineers working in this program. If you count all the people who support the facility, all told, it's probably close to 1,000 people in this program. And we do lots of things on the facility. We do fundamental science. You know, facilities like NIF have invented a whole new field of study called laboratory astrophysics. So the way astrophysics was traditionally done is you look at the universe, objects in the universe, and you make inferences about them, and then astrophysicists create models. We can create conditions in the laboratory that are similar to those seen in the center of giant planets or an exploding supernovae. So we now have astronomers and astrophysicists who come to our facility and work with us to study the detailed physics of these objects they're observing in the universe, which is pretty cool. We are studying all sorts of interesting material properties. You know, materials in these extreme conditions generate all sorts of interesting new properties for us. And so the facility has been a real boon for material science. And this program, over its 60-year life, has generated incredible technology spinouts. You put these really hard problems on the table, you get great people who come to work on them because they're extremely challenging, and they learn, ways to use the technologies in other unique applications. So, the team that worked on some of these early laser systems was part of the team that invented extreme ultraviolet lithography. So that's a direct spin out from this program. One of our researchers invented microwave impulse radar, which is that annoying beeping sound when you back your car up and keeps you from hitting things. They invented a technique to use lasers to peen or condition metals. So if you fly in an airplane, chances are the jet engine blades were conditioned by laser peening. That was a researcher from Livermore. So, you get many things from these endeavors that you didn't anticipate on the front side.
And what is Livermore's funding, and where does the bulk of the funding come from?
So the bulk of our funding comes from the National Nuclear Security Administration, which is part of the Department of Energy. So the Department of Energy is a complicated organization, right? So it does, this NNSA component is the steward of the nuclear security capabilities for the national security community. So that's non-proliferation, counterproliferation, counterterrorism, emergency response, in addition to the core nuclear weapons mission. And they support the facility because the facility was built to do national security science. So that is our goal. It turns out in this near term, the goals of the National Security Program and the fusion energy program are the same. Mm-hmm. We want to increase the yield of these targets because we want more energy coming out so that we can study the physics and begin to understand how these processes work in much more detail. And so for the next 5 years, say, the goals are well aligned. When you ultimately want to go down a fusion energy path, though, the needs are going to be different. And so we've been working with the Department of Energy to begin creating an inertial fusion energy program that can develop the component technologies, those highly efficient, high rep rate lasers I described, or how to capture and recycle the tritium that you need for these little targets, blanket materials that capture the neutrons that are released and turn them into heat so that you can drive turbines to make electricity, materials that can survive these environments, these very harsh radiation environments, and live in a power plant. And so DOE has begun investing. Last spring, the White House announced a bold decadal vision for fusion energy, primarily dominated by the magnetic fusion community. There are many private sector companies that are seeking to commercialize magnetic fusion approaches. And about $5 billion in private capital has gone into those companies.
And how sanguine are you about that?
It's going to be very hard. Mm-hmm. I think there's one school of thought that says they've had some breakthroughs in component technology, in particular superconducting magnet technology, that makes it more feasible to build a tokamak that can achieve break even or gain. It's not been demonstrated. And our experience suggests that when you move to the next scale, things happen that you didn't anticipate. And in plasmas, often there are, emergent phenomena, new types of instabilities or new complications that were not planned for. So I think 10 years is really ambitious, and the level of investment right now suggests that it's probably not very likely. Mm-hmm. The timescale for inertial fusion really depends on the amount of money that goes into it. So we'll see.
Yeah, you said in a news conference right after it happened that we're looking at decades. I loved how you said this, not 6 decades. I think not 5, which is what we used to say. You said, I think it's moving into the foreground and probably with concerted effort and investment, a few decades of research could put us in a position to build a power plant. Does that still ring true? Mm-hmm.
And it really is, how do you bring together a critical mass of people and ideas and technology and resources to make this process go very fast? And we're somewhat distant from that at the current moment.
Before we get into the general questions, I do have to ask you about your career as a woman in a field that has not historically been all that friendly to women. Women have made strides in some parts of science, not all of them. I think they've lagged behind obviously in computer science, which is a big problem. Mathematics is another problematic field, and physics. So how did you do this?
I'm gritty. No, you're right. I mean, representation for women in physics with PhDs today is not that different from where it was when I was in graduate school. So it was probably around 15% then, and it's closer to 20% now. And in plasma physics within physics is one of the areas with the lowest representation of women. I really did not intend to be a physicist. So I went to college fully intending to be a lawyer. I had wanted to be a lawyer forever, was really interested in public policy. I wanted to work in the government, and
Here you are.
so I was going to major in political science. And I talked to some lawyers, and they said, well, you should get a technical degree, because if you get a technical degree, you can consider pursuing opportunities like patent law, which you wouldn't have access to otherwise. And so I said, okay, that sounds good. And I'd been good at math and science and was being encouraged to go into a STEM field. So I thought, okay, well, what do I like? What kind of science do I like?
And you were encouraged by whom?
High school teachers, particularly my high school calculus teacher. He was great. What kind of science do I like? Well, let's be honest. I didn't like biology because there's too much memorization involved. Chemistry is just too complicated. I'm a simple person. And I'd had 1 year of high school physics taught by a biochemist, interestingly enough. And I loved it because there's a very small number of rules from which you can derive everything. And I really liked that building from the ground up view of the world. So I thought, I'm going to major in physics. And so I did, having really no idea what that meant or what physicists did or where this would take me. And I really liked it. And I really liked it for the reasons I just described, but also because it was hard. It challenged me in ways that other things did not. I loved literature. I love history. I'm still interested in political science and public policy, and I get to dabble in my current role. But that sense of challenge was really captivating to me. And then I got to do experimental science. And I learned out that I am an experimentalist by training and by temperament, sort of my natural state. And I loved building things and working with my hands and, asking questions of Mother Nature and allowing those answers to come back and learn that way. I just thought it was awesome. And so I came to grad school. I changed my plan. I was going to be a lawyer, and I decided, no, I'll get a PhD in physics. And the rest is history. I came to California.
I mean, it sounds good, but you must have encountered some kind of just maybe an obstacle or two.
Oh, or 10,000. It could be any of those numbers. I did. I was lucky in graduate school in that I met some amazing women scientists. So I had a very difficult experience with my graduate advisor at the laboratory. I was his first graduate student. First of all, that's a terrible idea. No one wants to be first. And I was not confident. I was not well prepared to go in and advocate for myself. And so I had an incredibly difficult time learning. My confidence was not being built up. My advisor was really not helping me. And we had a postdoc working in our lab a woman postdoc, who was just wonderful and became a great friend and mentor to me. And then we had another scientist come through and visit for a year. Turns out she later won a Nobel Prize, Donna Strickland, for chirp pulse laser amplification. Donna was another incredible mentor who really taught me to sort of get over myself, be honest about what you know, and really help me deal with the challenges I was having with my advisor and the environment I was in. And then a third woman scientist came and visited us, and I did the core experiments for my dissertation with her while she was visiting. But it was a really, really, really hard environment. I mean, I am stubborn and very tough, and that environment helped really create the kind of grit that got me to where I am today. But I wouldn't wish that experience really on anybody. I used to joke when I gave talks to the group that I worked in that I wanted to start by just going around the room and having everyone say, I'm the smartest person in the room. Because I was totally willing to stipulate that instead of just being attacked in what felt like very personal ways, not professional ways. In the national security community, I was often the only woman. I'm still often, one of a few or one of the only women. That's changed a lot in nuclear security, and it's changed a lot in the government. Mm-hmm. And so, I've always devoted myself in these situations to really taking my situation and trying to make the situation better for the person who came behind me, right? It sounds simplistic, but I was passionate about my work. I really was focused on trying to do the right things and trying to be part of this bigger national security community and purpose. And that was fuel for me as I went along. But I think today, I had a lot of tough experiences, and I was quite gritty, and I can't even imagine what it's like for someone who doesn't have that natural instinct to push back when you get pushed. It's still harder than it should be.
There's something called the Finkbeiner test. Do you know about it? So we actually did a whole episode on this for Lost Women of Science. A science journalist named Anne Finkbeiner, who'd been writing these profiles of women, of female scientists for years and years and years, and she said she just got bored. She just was so sick of saying, what the woman had run up against and what the husband did and how hard it was to do this and she said, I'm done. I'm not going to ever write a profile ever again that says any of that, not even the fact that she's a woman. And so we decided to kind of push back on her a little bit because we look at women in a historical context. Yep. But the New York Times wrote an obituary just when this whole Finkbeiner thing was happening, and of a rocket scientist, a woman. Do you know about this obituary? Mm-hmm. Who, and the lead, and it was written by a man. Not that there's anything wrong with that, but the lead was so-and-so made a mean beef stroganoff, and this was a rocket scientist, and so that turned into a big brouhaha. And the Times actually, the public editor got involved, and they had to kind of run a retraction of the lead, and came up with a new lead. So my question to you is, what do you think of when women like you, who are really public figures and represent women for the generation that's coming after you, do you think it's important to highlight the fact that you're a woman in a very not just in science, but in a difficult subset of science?
I think it still makes a difference to people, particularly the young women coming up. And I got a huge number of emails and people reaching out to me when I became director, because it was a visible sign to people that there were possibilities for them, that there were avenues that they now felt were open that they didn't feel were open before. And so I take, the need for role models is very real. People need to understand that there's opportunity. I had many, many wonderful male mentors over the arc of my career. I worked with mostly men who were very supportive and who really helped me, build my confidence, build my ability to manage tough situations. And so I take it very seriously when I find myself in a tough situation in a public event, to turn that into an opportunity to make, something positive come out of it. But
Well, pivoting back to, we have a bunch of technical questions.
Oh, great.
So,
Well, I see someone in the audience who can answer all of them. So, Bedros, you're on.
all right. Here's a really good one. Has NIF been able to duplicate the successful ignition result?
No, and partly because we have been unable to build targets of the quality that we need to ignite them. So a year before, so in August of 2021, we had the first high yield shot that told us we were getting close. We achieved 1.35 megajoules of yield. And then we set out to repeat that shot, and all the subsequent shots came in around 500 or 600 kilojoules of yield. They didn't come close. Because the physics changes very fast in this realm. So they can go up if all the conditions come together just right, and they can go down. Eventually, we began to get routinely above a megajoule yield. And part of what we learned in that is that the quality of those little capsules really matters a lot. After the December shot, we were waiting for the next batch of good diamond capsules, and the first group of capsules that we got our hands on failed target assembly. So they have a little tiny tube that goes into the capsule that puts the deuterium and tritium fuel in. That's about 2 microns in diameter, so about a 50th the diameter of a human hair. And the tubes fell out of those targets. So the quest continues to get another good batch of these diamond capsules and get them assembled and repeat that shot. But we have a series of experiments teed up to do just that.
Next question. I'm not even sure I understand it. Will fusion energy be utilized to recycle or reduce nuclear weapons?
No. So the beauty of fusion is it doesn't use any fissile material. It only uses the deuterium and tritium fuel, very small amounts of it. And in a good fusion energy system, you have to recycle the tritium, capture the tritium that's released, and recycle it efficiently to make the system work to be economical. But it is baseload generating energy, and that's why it's so exciting, right? So fission plants are great because they can produce stable baseload power independent of the local conditions. And fusion could serve the same purpose, but without the long-term waste considerations and different safety envelope than the considerations that go into commercial fission power.
Since the military has the ability to target something as small as an individual anywhere in the world, are nuclear weapons necessary?
So I think what I would say in response to that is nuclear weapons exist. And they exist in the hands of people who've demonstrated a willingness to use them. And the U.S. cannot be in a position of being coerced by others, right? It's like any technology. There are many technologies that have good uses. Biotechnology is the current one we worry about the most, that also have a dark side in the hands of the wrong people. And so I think we have to be clear-eyed about what the nuclear security environment really looks like. The stockpiles around the world have drawn down a lot since the height of the Cold War. But the threat from emergent proliferators or from other nations that are seeking to compete in this realm is very real. And the U.S. nuclear deterrent maintains stability in that environment. I know it feels a little counterintuitive, but that really is very important. And so, I hope we get back to a situation where we have viable arms control agreements again. I hope we can move to a more tri-party arms control regime that includes China in addition to Russia. We continue to develop new technologies that could be used for verification of treaties, et cetera. There are a lot of things that we hope will be possible, but the political conditions don't exist today to move forward on those fronts. But we, the people who understand our nuclear weapons understand other people's capabilities, and also understand the tools and technologies required to do things like arms control, non-proliferation treaties, et cetera. So we have a large cadre of people who are promoting nuclear security across a broad swath of applications.
Do you know how much progress the Chinese and Russians are making in their fusion efforts?
So the Chinese haven't actually built their next large laser. They have a huge cadre of scientists and enormous investments going into all sorts of areas of strategic science and technology, including fusion. And so they certainly have the capacity and have demonstrated the will to continue down this path. But the U.S. has a very substantial lead at the current moment in inertial confinement fusion because we got our facility built first and were successful in this first demonstration.
What is your scientific view of cold fusion?
That it's not fusion. It would be nice to believe that there were an easy way to get to this, but I think researchers have looked in great depth into the work that was done on cold fusion and largely debunked that work. So
I'm going to save this one for last. Could you? Oh, it's a good one. Could you please touch on supply chain issues? How the industry could start to take part in building success in the fusion world?
Yes. Supply chain is an enormous challenge for everything that we do. And I think the experience of the pandemic really brought that home for us. We become so dependent on these very international and tightly intertwined just-in-time delivery supply chains, not really a very stable system. So for commercial fusion power, for inertial confinement fusion, some of the early technology components are the laser technology. Several companies have already formed to pursue inertial fusion energy schemes, and they're focused on initially working with us on the target physics, because we have the only place where you can do the target physics at scale. But within the companies, things like the laser drivers that they might use or other technologies they might use to create the energy source for the power plant. And working in partnership on some of the things I described, like the materials challenges for fusion environments. So we have 3 inertial fusion energy companies that we're working with. There are quite a large number of fusion companies, private sector fusion companies working in magnetic fusion or other hybrid approaches. Some are more plausible than others, but there are a few that are really hard at work. There's a company called Commonwealth Fusion that's spun out of MIT that's hard at work building a tokamak system that they believe is one step until they begin work on a demonstration power plant.
Is that a spin-off of?
Spun out of MIT.
Interesting. How did the last administration's Department of Energy impact your programs, and what about now?
It was very interesting being a scientific organization in the midst of a political administration. So a lot of things changed. The beauty of the DOE National Laboratory System is that we largely stay the course in terms of our research foci, independent of swings in where the administration is going. Within the department, the biggest changes tend to be in the applied energy technology offices. So there's a office of fossil energy, there's a office of electricity, office of nuclear energy, energy efficiency and renewable energy. So you can imagine which direction, like nuclear energy and fossil energy went relative to energy efficiency and renewable energy. in the Trump administration vice the Obama administration. So those swings tend to be quite large. The labs tend to be pretty steady in doing the supporting science across all of those energy sources. So the biggest impacts we saw in the last administration were around things like our climate research programs. There was some consternation around those, although all the research continued through that period.
Is that because bureaucratic wheels turn slowly and the lag time was enough that you could keep going? Or?
I think for the research programs, it's easier to keep them going because you can think about how you frame the research portfolio that you're working on, how you talk about it, the language you use around it, the priorities, the ultimate applications for the work. In the hard technology programs, I remember, there was a lot of focus on fossil fuels and clean coal. We talk about clean coal, but coal is not clean.
Clean coal?
Clean coal. We have long history. We have a long history in technologies like carbon capture and sequestration. Again, it's actually a direct outgrowth of our national security expertise from nuclear testing. We understand the subsurface very well. And so programs like that are sort of bipartisan in nature, right? We have a huge amount of fossil fuel infrastructure. It will not disappear. So how do we manage it? How do we manage carbon in the environment better? How do we make things like carbon capture economically viable? How do we demonstrate them at scale so they can be part of this transition that we're trying to go through? And actually, this administration has supported, sort of as a point of continuity, has supported trying to move to real demonstrations. We have technology approaches. Can we actually take them out in the field and see how effectively they work? And that's what begins to bring the cost down. So
I want to link that to this next question without getting you in trouble. So as a manager, so in that environment of the previous administration, as a manager, what steps did you take to enable and facilitate the scientists who created the fusion ignition?
So because that's a core component of our national security programs, that program has done pretty well. And actually science and R&D have got pretty good bipartisan support in the Congress. And so those core R&D programs have done pretty well across different administration priorities. We try to take the long view. So we have internal discretionary R&D dollars called Laboratory Directed Research and Development. We use those dollars to build capabilities, to explore new ideas, to open new avenues to research, to bring early career staff to the lab. So that's one way we can, sort of mute oscillations in priority is by ensuring that we have resources available to make sure that what we know is important is still there. And, honestly, our job is not just to wait for the government to tell us what to do. Our job is to create capabilities in advance of need. So the labs were created as long-term stewards of capabilities on behalf of the government. We're federally funded research and development centers, which means we have a special relationship with the government where we can work in close partnership, free of conflicts of interest, learning about the problems and challenges that the nation faces, and then using our intellectual capital to create solutions, capabilities with this longer term perspective.
And a national security question, are the specifics of ignition going to be publicly available for other countries? They're asking, is it classified?
No, we publish as much of our science as possible. Part of a healthy scientific ecosystem is that it has to be open and engaged and connected. There are many more people, ideas, tools, technologies outside the borders of the laboratory than inside, and outside the borders of the nation than inside. If you look at the people in our program, they come from all over the world. They come to work with us because we have the best tools, the best capabilities, and the best environment for innovation and R&D in the U.S. Historically, that's benefited our country a great deal. So this program is, by and large, open science. There are, of course, we do classified research at the laboratory, and we do technology development that we don't share broadly for a whole host of reasons, export control or economic competitiveness or, other reasons. But for the science to be good and the science to be right, it has to see the light of day. So I did get asked at the press conference after we made the announcement with the Secretary of Energy. Someone asked me, said this shot happened on December 5th, and it's now December 13th. What have you been doing? I was like, I couldn't even imagine. What's the conspiracy here? What could I possibly have been doing? Like sweeping neutrons up with a broom and a dustpan. We were like analyzing the data and checking the data and asking other people to check the data. If you generate that big a neutron blast, it's pretty unambiguous. So we're pretty sure something happened. But, getting it right before you stand up and blather to the whole world is important. So just saying.
So the next to last question, in what ways might AI accelerate the insight needed? So
AI and machine learning are changing everything about science. I mentioned all the different diagnostic capabilities we put on the laser facility. They generate tons and tons of data. People can assimilate some of that data and use it to advance our models. We use things like machine learning and AI to bring all that data together to train our models to be smarter, right? So we still have to understand the underlying physics of this system to really create predictive capabilities. But we can guide our learning by using things like machine learning to much more rapidly ingest and analyze that data. So we've been doing that in a whole host of fields. ICF has been one of the big applications for us because it is open science. We can create curated data sets and allow others to look at those data sets, again, to use different types of machine learning and AI approaches on them. So it's becoming a bigger deal for us.
Mm-hmm. And here's this lovely last question. If you could wave a magic wand, what would be true in 5 years?
I'll take that to be related to fusion.
Oh, yeah, good point. It could be anything.
Yeah. Then in 5 years, we had a stable $1 billion a year investment in fusion energy. I mean, if we had $1 billion a year, we could really do something. So,
versus what it is now, which is?
So the actual line for inertial fusion energy, which is really the energy program, is $15 million right now.
Oh my God.
Now, there are other investments. There's investments in some materials things and other things, but it's well below the threshold of where we need to be to achieve a bold decadal vision in fusion energy. And so I'm excited for us to capitalize on this moment and really drive the kind of public investment that's needed to make this go.
So what would it take to get to $1 billion?
Let's see, $985 million. It really would take us creating a vision that the Congress can believe in, that the community that provides these precious resources to us can understand, can measure progress against, and can believe will be well expended. And so the fusion energy budget, fusion energy sciences budget, so that's an office within the Office of Science at DOE, is authorized to $1 billion total, but that includes the ITER project, all the magnetic fusion energy research in the US, a whole host of other things. So the amount left at the end for new fusion applications is very small. So we need to grow that investment. Investments in R&D pay long-term dividends. And there is a huge and enthusiastic fusion caucus in the Congress that I think as I said, if we give them the right vision for what's possible and a credible path forward, we'll start to see that number go up.
Well, on that note.
Or a bake sale. A really big bake sale.
Right.
One of those two has to happen.
I
I do make a mean beef stroganoff, by the way.
Oh, really?
And sourdough bread. During the pandemic, I thought it was required.
We'll make sure that'll make it into your obit. Well, I would like to thank this audience. The questions have been really great, both online and here in the audience. We could go on so much longer to talk about all kinds of things, but it does bring our program to a close. And I would like to actually thank you from the bottom of my heart and on behalf of all the women who have been lost to history, who we're trying to sort of save one by one. We have a big job ahead of us. So please listen to Lost Women of Science, the podcast.
Yes.
And thank you, Kim Budell, for being here tonight. And again, a thank you for the Commonwealth Club for hosting us. I'm Katie Hafner, and this program is officially adjourned.